Let us discuss about measurement of pressure using mechanical instruments in this lecture. We have looked at a pitot-static tube earlier, but not very closely. So, we will do it this time now. We will have a closer look at the pitot-static tube. So, you can see a close up view of the pitot-static tube here. As you are aware, there is a port right at the tip of the tube, and then there are several ports circumferentially located on the surface of the probe, some distance away from the tip of the probe. Let us go through the bullet points. The pitot-static tube is essentially a slender tube aligned parallel to the incoming flow to minimize disturbance to the flow, and the pressure is measured by several tappings in the same radial plane, and therefore, the pressure reading that comes from those tappings are basically circumferentially averaged. As you are aware that the port at the tip would sense the stagnation pressure, and these ports some distance downstream from the tip would measure the static pressure. Flow in the immediate vicinity of the tip undergoes a local acceleration. So, when the flow moves around the tip, apart from the stagnation streamline, which basically stagnates at the tip, the other streamlines move around the surface in a three-dimensional sense, accelerates and crosses that region, and then the velocity becomes more uniform, and after a while it reaches the stagnation port region. Now, if we look at the static pressure probes or the ports very close to the tip, what will happen is that they will record significantly lower pressure than the true value, and therefore, you have to locate them some distance downstream. Typically, they are located about 6 diameters downstream of the tip and also 8 diameters upstream of the stem. So, after the corner, you have a vertically upward moving stem. So, we are talking about 8d distance with respect to the stem and about 6d distance from the tip for the location of the static ports. Flow around ellipsoidal nose designs. So, we are now talking about the geometry of the nose, separates later than around hemispherical tips, and thus the former are less sensitive to yaw. So, if the tip of the probe is not aligned exactly with the flow direction, but is at a yaw angle with respect to the flow direction, then what happens to the reading of the probe? So, that is what we are trying to discuss over here. Depending on what kind of yaw angles it has, there could be some error. As long as the yaw angle is less than 5 degree with respect to the incoming flow, and if the incoming flow is a turbulent one, then the error in the Cp that is measured is about 1%. If the incoming flow is laminar, then the yaw angle needs to be even lower than 5 degrees in terms of error with respect to the free stream. So, these are very, very important issues with respect to the placement of the probe, the orientation, etc., and the designing of the probe based on the distances with respect to the tape to the stem as far as the static ports are concerned. Now, let us look at a situation where we insert this kind of a probe inside a converging diverging passage and we traverse the petrostatic tube through such a section. Let us say you have a vertically oriented test section of a wind tunnel and you have liners placed inside the test section. Let us say the liner looks like this. So, you are going to have them symmetrically disposed on the two walls of the tunnel, and of course, we are talking about a low speed wind tunnel. So, this should not be confused with the converging diverging passages that we talk about in supersonic wind tunnels. And let us say you have some system by which you can locate the probe at different axial positions by means of some kind of a probe traversing arrangement. Remember that the flow is coming from the top downwards, and obviously because of the liners the flow is having a variable velocity. So, it accelerates in the converging section, then this is a constant area section where it remains constant, and then it decelerates in the diverging portion. Also, the angles that these converging sections and the diverging sections make with respect to the axial direction need to be related like this, because as you know the converging section can have much larger angles, but the diverging section cannot because of the adverse pressure gradient issue in the diverging section, which can lead to flow separation. So, we would not like the flow to separate, we need it to be attached and we need to traverse the probe along the axis. So, let us say the axis is along the x direction and the normal direction is y. So, the probe traversing arrangement could make it move along x or it could also make it move along y. So, such arrangements can be designed and attached to the wind tunnel test section. So, if you do that, the flow along the axis can be considered to be by and large inviscid, because you are far away from the boundary layers which are developing on the surfaces of the liners, and therefore, it is inviscid. It is also considered to be incompressible, it is irrotational. So, the Bernoulli's theorem that you have learnt about should be valid if you move from point to point. So, in that case, let us not mark this as P infinity. So, point to point, if you measure the P naught using this probe, you will find that the P naught will be more or less constant. So, what we are talking about is locating the probe at different x, y stations and trying to monitor what P naught is. So, you should be able to see that P naught at x 1 is nearly the same as P naught at x 2, nearly the same as P naught as at x 3. So, which basically would show you that Bernoulli's theorem is approximately satisfied as long as you are moving through the central axis where the flow is by and large a potential flow. Additionally, if you look at the static pressure variation, you know that the static pressure variation will be happening in a way that is kind of inversely related with the velocity. So, the highest pressure drops, the static pressure drops would be in the lowest cross sectional points. So, in that case the pressure will dip, the velocity will increase, and pressure dips when area reduces. That is the kind of variation you should be able to see in an experiment like this. So, This is a typical problem in which you can make use of a pitot-static tube, make it traverse, move from one point to the other through a converging diverging passage or a venturi tube in a low speed wind tunnel, and thereby do these kind of experiments and test. A very fundamental entity in many of the aerodynamics experiments are pressure ports, which we locate on a model, on the walls of a wind tunnel, and many other locations. So, each hole, each port on the wall alters the boundary conditions of the flow, which is very well elucidated in this figure. So, we are actually zooming very close to the cross sectional plane, where a small port is shown with much more details, and it produces a curvature of the streamlines, and hence the pressure changes in its vicinity. So, as the hole size decreases, the effect also decreases, which is quite intuitive. Usually the streamlines which enter the hole, they raise the pressure, and in some cases the separation of the stream on the leading edge of the hole causes a decrease in pressure. The size of the holes of the static pressure must therefore be smallest possible, because these the way the streamlines are affected, the way the neighboring flow is affected by a port or a hole increases with the size of the hole. So, there could be a rise, there could be a fall in the local pressure, and which is unintended. Here are a few typical characteristic dimensions which are mentioned. There could be a small burr, for example, at the tip of the hole, which is basically a manufacturing defect, and such a manufacturing defect is basically shown over here, where you can identify that the whitish portion next to the hole periphery is basically the signature of a burr, which is left behind as a part of the manufacturing process, whereas here it is nicely shaped, so that it is not left with a burr. Now, we are talking about a pressure change in the neighborhood of the hole, which is non-dimensionalized with respect to tau w, which is basically the wall shear stress, giving us some kind of a non-dimensionalized parameter pi, which is a function of many parameters which are dependent either on the flow, like the Mach number, or on geometrical details related with the port. So, the ds is the tapping orifice diameter, u tau is the friction velocity under root tau w by rho, d is the flow length scale, which is a characteristic length scale of the problem. M is the Mach number, Ls is the depth of the orifice, dc is the diameter of the cavity behind the orifice, that is this orifice which is below. Epsilon is the root mean square height of the bars on the edge of the tapping orifice, which is a very, very important issue in terms of the finishing, the manufacturing finishing. Rho is the fluid density, nu is the kinematic viscosity, etc. If you watch carefully, these parameters all figure here in the non-dimensional groups, and the true pressure at the wall, if we represent it as Pw, is then given in terms of the measured wall pressure, M for measured, through a relation like this. So, as you can make out that the measured wall pressure has to be modified by using the pi function, which is dependent on so many non-dimensionalized groups, and therefore, you end up getting a functional connection between the measured pressure and the true wall pressure. So, you may actually need to calibrate things before you get a functional relationship in place. This is a very, very important reference where you might find lot more details regarding these topics. Next, let us look at manometers, which play a very vital part in the group of mechanical equipments associated with pressure measurements. whether it is a high speed flow measurement or a low speed flow measurement. Here we are talking about a vertical manometer using a low density liquid. It may be water or it may be a liquid which has a specific gravity lower than 1 as well. There are a lot of proprietary liquids which are also used in this world of manometers. What we are looking at is what is called as a gang manometer, where we have a number of manometer limbs available, so that we can simultaneously acquire pressure from many points, which can include pressure probes, which can include pressure ports located on models, etc. That means, the advantage is simultaneous acquisition of pressure from many points. Let us have a quick look at the morphology, the main elements of a manometer. So, a very important component is this fluid reservoir, which contains the fluid. Here the fluid happens to be a proprietary fluid which has a color, red color, and the fluid also has to have favorable properties. One of the important properties is that it should not wet the glass within which it is placed. Fluid reservoirs which is containing the fluid, and it is most often open to atmosphere, and you can make this fluid reservoir go up or down along this metallic rod. You can slide and locate it, fix it in a certain position. That fixes the level of the liquid in the manometer. That means, at what level these limbs will have the manometric fluid is basically dependent on the height that you adjust of the fluid reservoir. There is a common bottom tube, basically a metallic tube at the base of the limbs, and the limbs of the manometer essentially get the feed of the manometric fluid through this common bottom tube, and this bottom tube is connected to the fluid reservoir. On top of the tubes, you have adapters to fix the pressure tubes which are coming from the probes and model pressure ports. So, you essentially fix the tubes here through which the pressure is basically fed. Now, you can figure out that this green elliptical zone is showing 3 limbs where the height has changed. So, you can intuitively make out that there are pressure tubings which are fitted to these 3 ports, and which is the reason for the change in their height. You can see that the other limb heights are all constant, and they are essentially open to atmosphere. Lower the level, higher the pressure. You have a frame on which multi-tube stack of these manometer limbs are mounted, and they can be pivoted together, so that the whole setup moves to a different inclination and it can be fixed. There is a disc like structure over here, where you can you have dowel pin like arrangements, where the inclination may be changed and you can pin it to a certain orientation. Once the orientation changes, we will discuss about it soon, the sensitivity of the manometer would change. You will have enhanced sensitivity if you tilt it, if you incline it, and it is required for certain purposes. You are seeing a typical inclined tube manometer, but a single manometer which is fixed to the settling chamber or stagnation chamber of a typical low speed wind tunnel. You can see the fluid reservoir here, you can see pressure tubings which are connected to the ends of the manometer, and they are going to different points in the wind tunnel. So, you have a wall static pressure here, and some other tube is going to other points in the wind tunnel from where you are making certain measurements. Why do we say that it is going to make it more sensitive when we discuss about inclined tube manometer? So, in one situation you may have the manometer like this, in another situation once you tilt it, it may become like this. If it is the same pressure that you are measuring or feeding to the two tubes, the liquid will essentially rise to the same height. So, if this is your datum, then the delta H in the vertical sense will be identical for both cases. But the markings that you have on the scale, if you look at them, the markings go like this. So, let us say this is 10, 20, 30, 40. So, if this is 40 from the datum, the same markings might give you something more between 40 to 50 from the datum in the inclined case. That means, you are talking about the same pressure, but you are actually getting a larger reading or a larger change on your scale. That means, for the same change in pressure, you have a larger reading. This is essentially the issue of enhanced sensitivity. That means, the manometer in its inclined position shows you a larger reading for a small pressure or a larger reading for the same pressure that you are getting from a vertical orientation. That means, every marking on the scale now indicates a smaller pressure that it can read. Delta H, what you have in this orientation, is indicated on the scale as delta H by sin theta. Theta is this angle. Now, what is the advantage of that? Since sin theta for theta less than pi by 2 will be less than 1, this is a fraction which will essentially amplify your reading, and that is why it raises your sensitivity. So, when you are measuring very low pressures, let us say you are running this wind tunnel at very small velocity. Your fan is rotating at a very small RPM, and therefore, you have a very small velocity to be recorded. Naturally, the delta H will be very small as well. In order to have good accuracy in the measurement, what should you do? You should immediately incline your manometer and try to take the reading. Let us say if the least count of the manometer is 1 mm and you incline it at an angle of 30 degree, theta equal to 30 degree, then if your reading was coming out to be 4 mm using the vertical orientation, now the same reading will be displayed as 8 mm. So, for example, if you read it as 4 mm in the vertical orientation and now you read it as 7.5 mm in the 30 degree orientation, then you can figure out that this reading will be more accurate because you are able to amplify the reading with the inclination, and therefore, small errors committed for the vertical arrangement when amplified may be rectified in the inclined orientation. So, such advantages are there with this kind of a orientation change. Next, let us discuss about some special pitot probes which are called as the boundary layer probes. Let us see how we use them. So, you have to use the same probe a little more intelligently now. Let us say if you have a wind tunnel test section which is again vertically oriented, and you have inserted a thin flat plate you have a flow coming from top, the boundary layer is forming on the plate. Of course, it is forming on both the sides, but you are now going to insert a probe from one side and you want to measure the boundary layer velocity profile. This is a boundary layer probe. What is the specialty of this probe? Let us try to figure out. This probe needs to be having a very, very thin profile, so that it can reach very close to the wall if you were to look at it from the other side, you would see a profile like this. So, a thin rectangular tip where it senses the flow. Okay. So, that is essentially a cross sectional view of the tip. Now, if this is very, very thin, let us say this dimension is d, the closest that the center line of that tip it can reach the wall is d by 2. That means, once it touches the wall, then it will be at a distance of d by 2 from the wall. That is the basic idea. The fact that d is very small would mean that the probe will really reach very close to the wall in the sense of the center line of its tip. So, initially you traverse the probe and make it just touch the surface of the plate. How do you do it very accurately? You have a traversing mechanism here. And you have a micrometer which indicates the location of the probe very precisely. Now, the tip of the probe essentially reads the P naught, the stagnation pressure, and as you move it from one location to the other by very gradually moving it away from the wall, you have the reading, let us say, at different y locations. So, let us say this is the x direction and the wall normal direction is the y. So, you have it right at the wall, then you have it at station y 1, y 2, y 3, etc. That way you keep moving it away and you record the P naught at 1, P naught at 2, P naught at 3, etc. Record the wall static pressure by having a different port located on the wall of the tunnel and record the P naught from the boundary layer probe. Whatever P or P infinity that you obtain from the wall of the wind tunnel, that is going to remain constant within the boundary layer. And if you were to measure the pressure at the surface of this plate by using a static pressure port, that would also be approximately equal to P infinity only. Also, within the boundary layer, this pressure would not change, because as you know from the boundary layer theory, del P del y goes to 0. That means, there is no change in static pressure. So, why does the pressure change at all within the boundary layer, which your pressure readings will finally tell you? it is going to change not because the static pressure changes, but it is going to change because the dynamic part of the pressure changes. So, at different points based on your P naught that you record at y 1, y 2, y 3 etcetera, you are going to get u 1, u 2, u 3 etcetera, and then finally, when you plot the u variation as a function of y, you will be able to get the u distribution as a function of y. So, this is your y 1, this is your y 2 etcetera. So, this is how the boundary layer probes are used for boundary layer velocity profile measurement, whether you do it for a flat plate or you do it for non-zero pressure gradients, which could be adverse or favorable. So, we will discuss about a few other techniques for pressure measurement in the upcoming lecture. So, in this lecture we could discuss about the pitot-static tube, we discussed about how that may be used for undertaking measurements in different experiments. So, we just demonstrated an experiment of a traversing pitot tube in a converging diverging passage. Then we talked about pressure ports, their utility. We talked about vertically oriented and inclined manometers, and we also discussed about boundary layer probe. In the upcoming lecture, we are going to discuss about Rayleigh pitot tube, which we could not complete in this lecture. Thank you.